In this demonstration, I'm going to show some applications of Rust into cryptography. So I'll try and show a basic setup of how we create a Rust program, some application areas, and then some of the key elements around a Rust program. So Rust is a relatively new language, and it tries to overcome many of the problems that we see in our existing languages, especially in C and C++, where we can have a problem with memory. This typically relates to the garbage collection and where there is poor management of memory. Within Rust, we have much stricter controls over the usage of our memory and how long each data element is allowed to exist for. So generally it's a bit tougher to be able to create a program, but once it's created, then it should be much more robust than existing languages. Another great choice is Golang, which is quite similar to the syntax that we would use in C and C++. But Rust is an excellent environment for creating code which is robust and also secure. And there's so many libraries that we can access. Okay, so I'm going to take you through some examples. So I'll try to pick up a few examples from this page here. If you're interested, all of the code and the applications and the sample runs are available on this website here. Okay, so initially I'll show the setup that I have. I use Visual Studio Code. I also use a Microsoft Visual Studio to be able to build web applications. But I find that Visual Studio Code is one of the best environments to be able to run and edit Rust programs. Okay, so you can do this with inside Visual Studio Code, but what I'll do is I'll actually create a new project. So let's call it my crypto here. Okay, you just go into your crypto folder, and then we say cargo, new, and we'll call it crypto. Okay, and it's actually created that for us. So within inside this folder, you'll see that it's created a cargo.toml and a source folder. If we go into the source folder, we'll have a look from there, and we can see there's a main.rust file. Okay, have a quick look in there, and you can see it's just a basic hello world that we have. Okay, so once we're in this folder, we can use a cargo build to be able to build the cargo, and then we have cargo run to be able to run it. Okay, so it's a very simple hello world program that we have in there. And basically what happens is that we create a target, and then in target there's a debug, and then we'll actually see within there we've got a build folder. We've got let me see, we have our crypto program here. So in debug we've actually created the program here. So when I run this program, I'm actually running the executable code. If you're running on a Windows environment, you'll see an exe there. I'm running on a Mac, so you'll just see the program as an executable file here. Okay, so that's the basics of it. We can run the program with cargo run. We can build it with cargo build. As we'll find, if we have syntax errors, then we can fix them in the environment. Okay, so this is what we get. If I open up the folder that I've just created in here, So I can open up that as a folder, and this is what you see. So in the source file, there's my little program there. The great thing with Visual Studio Code is it points you towards it. The text, the language, and it'll point you towards good things to integrate. So that's typically, we would get that from extensions. So you can see there's a whole lot of things that we can actually apply into our projects to help us with the code. But we'll just go back here just now. So the main file here is our Rust main program. It's a .rs in there, and we should find that is a pretty good syntax checker and helper as we go along, and we can initialize our variables and so on actually within here. We also see our cargo.toml, and the toml is the place that will add the dependencies that we'll bring in. They're called crates, not quite libraries, but we'll bring in a crate, and then we will actually define the dependencies in this file here. So that tells Rust what crates it needs to download to be able to integrate with the code. But there's the name of the file and so on, and the version and so on. But as I said, in the dependencies we'll have a version number for the crate, and we'll also have the name of the crate, and it will be downloaded. So the place that we often look for the crates is within here. Okay, so we basically find the crate that we're looking for. We'll get the version number of it, and we'll find all about the actual crate and the methods that are used within it, and then we'd often just put that into here, and then that will allow that crate to be downloaded and that version, and then integrated in with our cargo infrastructure. Okay, so that's the main elements of this. We would then just start to debug that if we wanted. So in this case, we're not getting that integration quite right because we have a syntax error in there. Okay, so we can then go ahead and we can start to build our project. So one thing that the Visual Studio Code does is that it will detect that it's a Rust program and that it needs to create a build for us. So you can see what's just happened there is that it's now created a launch.json file, and with inside that it gives all the details that we require to build our project. So the things like the building, cargo build, and so on, and run is actually defined in this file here. So now when we run this, we should find that it will run automatically in there. Okay, so within inside there, when we run now, it will automatically invoke the program. There's no errors in this program just now, so when we actually run it, it goes straight ahead. But most of the time we're going to have errors in our program, and for that we can look at the problems and we can try and fix the code that we have in here. Okay, so the program won't build until we've fixed all the problems. Sorry, we've fixed all the problems in there. So we'll just save that. Okay, save, and we can see here when we try to build that, then it's telling us that we've got some errors. But Visual Studio Code will give us a better idea, and we can see here there's the problems that we have there. So I just fixed this one here. That's the only problem I think that we've got, and we'll just save that there. Okay, so now there are no problems in there. Once we've fixed that, we can run from here. We can create breakpoints if we want, or you can just drop into the command line here and we'll rebuild. That's fine. You can see where it's been stored to here. And now what we'll do is we'll just run it from here. Cargo run. If we've got some arguments, then we can put them after those options. We'll just run there, and that's fine. So just to show that it is working, we'll just save that one, and then we'll rebuild it, and then we'll run it, and you can see the changes that we've made. Okay, so that's the basic setup of Rust, and it's Visual Studio Code is excellent for showcasing, for making sure that you're looked after in terms of the errors. The compiler responses are typically pretty good in terms of trying to debug where the problem is, but it takes a bit of experience to understand how to interpret these warnings and errors. Okay, so I'll talk you through a few of these examples. What I'll do is I'll use our Replit rather than using the Visual Studio Code, but it's actually quite easy to use one or the other. So I'll pick off some examples, and I've separated them into stream, encryption, block, RSA, elliptic curve, key exchange, and some other areas. So we'll make a start with probably one of the best encryption methods, and that's AES-GCM. So AES-GCM is an interesting method for encryption, as it gives us what's called authenticated encryption with associated data. Basically what happens with this is that we can encrypt, and then we add in some additional information, such as the port that a session is using or the session ID, and then we can use that to authenticate the actual ciphertext that we create. Okay, so we'll give this one a little try. So in this case we have a message, a key, and we have an initialization vector. We'll create the encrypted stream, add in some additional data. It creates a tag also, and then we'll use that tag to be able to decrypt and authenticate that this is the plain text for the cipher stream if we add in the authentication data. Okay, so this is the code here, and what I'll do is I'll just run this code through Replit to get an understanding of the scope. Okay, so we can see at the top here that I've got 4 external crates. So I'm going to use the crypto crate, base64, hex, and Rust serialize. Often, as I said, what we would do is that we would go to this docs.rs and find the crate that we require. So in this case, one of the crates that we're looking for is Rust crypto. If we search for that one, then hopefully we should get some details. It gives us the current version number. We don't have to take the most latest one. We could take an earlier one if there's any problems. But it also shows us what the dependencies are and the other libraries that we'll bring in. So we might not want to bring in some of the dependencies. We can make a choice as to what version that we're going to bring in. So in this case, here we have 0235 and so on. And we can click on and actually have a look at the methods that are used, and then hopefully understand the basic syntax of it. I'll try to explain what these elements actually mean as we go through the code. Okay, so you will typically integrate here. I'm using 2008 compiler of Rust because Replit doesn't support the latest 2021. So I'm using 2018 from there, and these are the dependencies that I have. Okay, so once they come in, they're defined as an external crate. Then what we have is that we will define the methods that we're actually using. So in this case, you see crypto, and then we're using AES-GCM, and we can get the method there that we're going to use, which is the AES-GCM code. We can then define any functions that we have within the code here, but our main program begins with the main element. Then we have the declaration of our variables, and these are automatically assigned by the type that we create for them. So the let allows it to be casted and also declared as a data type. If a variable is changing, we make it mutable. So if later on, if I use my add, then I will not be able to compile because it's a mutable. It's not a mutable variable. So something that's going to change, we make it mutable, which makes it allowed to be changed. Something that won't be changed, we don't put the MUT tag on there. Okay, there's various, I won't go into the detail of some of the data types and so on, but this is a string here, and we also get what are called vectors. So the vectors themselves can be strings, and we can move between a vector and a string element. The vectors are generally have a much larger scope than strings, and manage the memory better, because once you've declared a string, it's like a fixed array, it's like a fixed space for the string. Vectors are allowed to grow in size and are much better in their control. In terms of the print statements, then we just use like C code, the print line, and then when we have a variable that we want to display, we can put it between the braces in there. So this is going to show message in there. Okay, so we'll find that we can do our conversions. So if we want to convert from a string to a byte array, as we often do in our crypto code, we can convert it into there. So that's going from a string, our message string, and it will convert it into bytes that we can then use for our crypto. Okay, so we've got a key size in there. We're taking 128-bit key size for that. We can take 256 if we want, but we'll go for 128. We then bring in our structure in here, which is our AES code, and we're going to create a new object for that and define it as cipher. The data types here. This is a pointer to a byte array, so this is 8-bit values. Our nonce is our salt here. Again, it's a pointer to a byte array, and in this case we've got the key size there. So Rust will manage these very strongly, in that we can't get away with creating different data types and passing them as different pointers and so on where we cast. Very strict about that. Okay, so then we've got our encrypt method in here to be able to encrypt, and we're taking in some plain text as a byte array. Then we have an output, again a pointer to a byte array, and then we're getting a tag out. As I said, we're using AEAD to create our authenticated encryption, and we're getting that out as an output tag. Okay, then we can just decrypt, and this time we'll create the cipher again with the key, and then we'll do our decryption to give us our output from there. Okay, so if we just run it, won't go into any detail, you can look at the code when you've got time, But you can see here, here's our message. Let's change that message, if we can, to hello. And we'll put it as my additional data. So we would get, it wouldn't decrypt properly if we didn't have the correct additional data, in this case for GCM. So we just let that run, and we're using hello, we're using a key of just zeros. Obviously we'd use a random generator, a byte, 128-bit random generator there. Would also create a salt value which was random, but we'll just make it zeros just now. That's the additional data. The key, the encrypted ciphertext, is the same length as the message because it's a stream cipher that we're using, and you can see there that we've managed to successfully decrypt the string back again. With GCM there's no blocks or there's no padding or anything like that, so it's really quick, and we don't end up with any strange characters at the end. Okay, so if you've got time, have a look at the code and see if you can understand how it works. It takes a little while to get used to all the syntax and so on, but once you're over that, then you'll find it's a rock solid environment for developing our code. So let's see if we can actually find that folder in our with Visual Studio Code. If I can find it from here, there we go, GCM. Open the folder, and here we are here. Okay, so you can see that allows you to try different versions. That's the really interesting thing. It'll actually show the different versions of the crates that we want to integrate in there, and the code itself has excellent integration. You can see there that it's all color coded for you, and it's very easy to add in. You just need to make sure that you bring in the right crate here. Once you've got the right crate in, then you can actually in all of your structures that you need. And these are automatically added, so whenever you use one of these elements here, we don't have to do crypto AMGCS, GCM in the code. We can actually just put in the identifier here. So if we needed to, we could put in the full path there for that. If we wanted, we could do it like that, but it's going to look a little bit messy. So that would be the same as what we have, but because we've said it, we've added a use at the top, it knows automatically to take it in from that crate. Okay, so that's an outline of it, and you'll actually find that if we have syntax errors, then Rust and the environment will actually help us to debug those. Okay, so we'll have another look at another one. And here, in this case, we'll look at some symmetric key encryption. So we'll have a look at this ECB one here. ECB is less complicated than GCM, so it should actually be easier for us to have a look at this one. Okay, so same thing. This time we look at the cargo file, and we're using the AES integration for the code, and a few other things, including the block mode in this case, which is going to allow us to do the ECB integration. Okay, so we've got some uses at the top here, and to find a type, we're bringing in a message here as a string, and then same kind of idea that we have. We're using the encrypt method and also hopefully decrypt to be able to decrypt. Again, we're using these mutable variables. Wherever there is a change, and we're passing these values here for the byte array as a pointer. So just give that a little run and see if it works, and there it goes, it works using this key. There is no salt in this case because we're using ECB. There's the ciphertext. Because we're using a block cipher, that will be in chunks of 16 bytes with padding into it. So we've got to make sure that the padding is removed when we use it. Let's see if we can find this example within our code. And what we want is the ES one. I don't see it there. Okay, so that shows an example there. Okay, so let's try a little RSA program here. So with RSA, we create two prime numbers, we multiply them together to get a modulus. We then have an E value. We calculate a phi value, which is P minus 1 times Q minus 1. We take the inverse mod of E, a mod phi, to calculate D, which is our decryption key. We raise a message to the power of E, mod n, and then we decrypt by taking that cipher value, raise it to the power of D, and then take mod n for that, and we should end up with the same value. Okay, so we start off with value 55. We'll take two prime numbers, 67 and 103, and hopefully we'll end up with 55 again, which we do. Okay, so that's the basics of RSA there. So let's have a look quickly at the program that will create that. Okay, so I've got an inverse mod function for a value, and then a certain mod as I outlined. I've taken a first principles approach in that I've got a mod to the power of something, mod something else. And in this case, I'm using big integers. And the reason for big integers, sorry, this isn't big integers, this is U 128-bit. So in this case, we'll use 128-bit unsigned integers to be able to create it. The problem with that is that it won't take too long before we overflow the 128-bit if we're using a very large prime number. But it should work up to a certain level. Okay, so I'm declaring these as 128-bit integers. So you'll find that when you create your integers, they will automatically be given a type defined with the value that we assign it to. In this case, it's likely to be assigned an integer, 32-bit or a 64-bit. When we're using the environment will actually show us what that type actually is. So you can see here, the type is displayed after the variable. You can see here, this is a type ampersand U18, which is a byte array. So when we say let p equal 32, we can see here it's been automatically casted to an integer, that's a signed integer, 32. If we want to make sure that we cast it to something else, we must put in something after the colon there. Okay, so now P is unsigned 128-bit. If we had left that off, then it would have been an integer 32-bit. So it's important that you see what the little grey text is showing you, because that will actually define the type of the data type. In this case, we're making sure that although it looks like a 32-bit integer, it's actually a 128-bit integer that we want to use. Okay, so in this case, very simple, P and Q, we multiply to give n. It's not mutable, so it's not going to change after we create it. There's the E value, and we take m to the power of e mod n. So this is a little first principles method to do the exponential. It's a standard way that we do it. We go through each bit. It's called Montgomery methods, and it allows us to very quickly create an exponent, m to the power of e mod n. If we did this just with m to the power of e, it would take a long time to do that, and it would probably overflow the machine. This is the very efficient operation there, where we're taking m to the power of e, but we're knowing that it's going to be mod. Remember, mod is the remainder of a division. Okay, so then we calculate phi. We then calculate the inverse mod of e, mod phi, and to create d. D becomes our decryption key, and that's our private key. E and n are our public key. D and n are our private key. So then for RSA, we take the cipher, raise it to the power of d. In this case, we've got to recast d because it comes through here as a value called isize, a type called isize. So we've got to recast it because Rust won't allow us to be able to pass variables that are a different data type. If we tried that, then we would get an error in our compilation where it's telling us that we can't do that. It's expecting isize, so we would go in and we'd modify it to pass it in as a 128-bit unsigned, and hopefully now everything will be okay from there. Okay, so that works perfectly. We can run it as a command line if we want. So cargo run. So I think I've set this one up to pass 3 values in. The message, the p value, we'll go for 97 is my favorite prime number, and 101. Okay, so we can pass the values in through the command line when we're running it in there. Okay, so that's an example of using RSA. So bare bones RSA in real life would be more complex than this, but this just gives you a basic example of how RSA actually works from there. Okay, so that's RSA. We'll have a look at some elliptic curve methods. So let's see if I can find an interesting one here. This one is creating ECDSA signatures with P256. So there we go, we've got some data. We want to create a signature as we would in Bitcoin and Ethereum using ECDSA. This is our signature here. We then check the signature against the private key, and to make sure that this has been signed properly, and it has. So in this case, we create a private key, a random private key, 256 bits, and then we create a public key. The public key is used to verify the signature. The private key is used, this is the verifying key, and the signing key is the private key. So when we sign, we use the signing key, the private key. When we want to verify the signature, we use the verifying key or the public key. Okay, so let's have a look at the code for this one. Okay, so in this case we're using P256, and we've integrated it in here with hex and also with the rand core, which gives us a random number to create the private key. Okay, so I'm going to create a message. From there, I create my signing key as a random number here, 256 bits. I then can generate the verifying or the public key from that signing key. It's the way the elliptic curve works. We create a random number, 256 bits, and then we create a base point. We add the base point the number of times in the private key, and it'll create a public key for us, or our public key here. Okay, so this then creates a point on the elliptic curve. That's our verifying key in there, and from that we can sign a message with the verifying key. After that, We can then verify the signature using the public key from that, and then hopefully everything will work out okay there. So give this a little run just to see if it works, and well, it does. There's the hello world, and we can verify the signature. The return that we get here will actually define if it's a true signature or not. If we wanted, we could put in the wrong signature, the wrong message in here, and then when we try to verify the message, we can see here that the message is incorrect with the word hello in there. Okay, so that allows us to be able to check for ECDSA signatures. Okay, some of the other ones that we've got in there, some more complex ones to do with crypto pairing. And what I've done is I've integrated some of the Miracle code for crypto pairing. This one relates to Signcryption. And again, the great thing is that it's fairly easy for us to be able to integrate our libraries, in this case from MCore, which is the Miracle libraries, and then use this inside the code. Okay, so that's given a quick overview of using Rust and some of the cryptography. You should find all of the examples on this page here, and hopefully you can get them set up inside Microsoft code.